Okay, so we're starting the unit on waves and sound. In this unit, you can see I've got sound wave here, only the best transformer ever. Uh, but you can debate that if you want. Anyways, this is the old school one where he was a tape deck and stuff like that, which is pretty cool. Used to have that as a kid. So anyways, we're not talking about this kind of sound waves, but what we're talking about is waves in general, what they are, and what sound is and how it travels and things like that, and the speed of waves and their properties. Really, really important because light, sound, water, earthquakes, gravitational waves, everything is waves. And all medical equipment these days is all about waves and sound. If you get ultrasounds, if you get MRIs, anything. Microwaves have, they're obviously some form of light waves that are in there. The signals coming out of your phones, Wi-Fi signals, cell tower signals, that's all light. It's all waves. Everything, absolutely everything is waves. You're going to find out later in grade 12 about particle waves and electrons behaving as waves and as particles. It doesn't stop. And there's some key aspects of waves that you're going to be using this in biology, chemistry, physics, engineering, radio communication, like radiation therapy. If you go to be a doctor, you have to learn about all this stuff. It's so important. So of all the units, this one touches and hits on so many different aspects of your potential future lives and just the world and the universe in general. So in this unit, we're going to learn about transverse waves. We're going to learn about longitudinal waves, what a medium is, what the speed of waves are, what the speed of sound is, some really important properties like constructive and destructive interference. A lot of you have really fancy headphones that have noise canceling headphones. And this is a form of destructive interference of waves. Fantastic. It's based on what's called the principle of superposition. So this fancy word is really just constructive and destructive interference summed up as one thing. Literally, the word summation is the word for superposition. It's similar. We're going to learn about the energy that waves carry, what periodic motion is, frequency, pitch, wavelength, amplitude, what's something called the universal wave equation that's really important, a concept called resonance, beat frequency if you want to um, tune an instrument and things like that. You can talk about how beat frequencies are forms of constructive and destructive interference that allow you to tune an instrument. We're going to talk about what rarefaction is, nodes and antinodes. These are really cool. Reflection, transmission, electromagnetism or light, matter waves, mechanical waves. Really cool effect called the Doppler effect. It's a really neat concept. You've probably all heard about it before. It's that or sounds that you get when objects are making sound and moving relative to you, towards you, or away from you. The Mach number, really neat idea about objects traveling at Mach 1, Mach 2, or Mach 0.5 or Mach 7. I know the SpaceX just sent up a rocket recently. I think it was the Dragon, I'm not sure, with Bob and Doug in it, which is pretty funny. And those things travel at Mach 10 or something like that, or maybe even more. I'm not even sure. I'd have to look it up in terms of the speed of sound. So they're ripping through the air at faster than the speed of sound, like 7, 8, 9, 10 times the speed of sound. We'll learn about what the sound barrier is, what supersonic, subsonic means, and how echoes of sound are really just the reflection of waves. So that's super important, and that's what we're going to be focusing on in this unit. Okay, so you've downloaded the waves and introduction document. Here's where you're going to be able to draw in and follow the PowerPoint presentation. You can pause it, write in your information on the sheet as we go along. Now, I'm going to have to skip some of the investigations. I'm just going to cover all of it in this unit, in this presentation. And, back in the class, we can look at all of this in real person, like in real life. Okay, so let's get started and see where we're at. All right, waves, and follow along with that sheet. Some of it's maybe a little bit out of order, so you have to pause and rewind a bit, but that's okay. An introduction to waves and sound. All right, so what is a wave? Well, simply put, it's a disturbance or vibration that transfers energy progressively from point to point in a medium. So it requires, or not all waves, but most waves, the vast majority of waves require what's called a medium. That's a material. So that word, that medium is a material that the wave transfers through. It's the way that you pass the energy through the particles in the medium, and that energy transfers through the medium at some particular speed, a very particular speed, in fact, based on the composition of that medium. So the mediums can be anything. It could be a piece of wood, it could be the earth, it could be water, it could be a string, it could be a tight string, it could be a loose string, it could be a slinky, anything like that. Anything that you can transfer energy through is a medium. A guitar string, like when you pluck it, the energy transfers from one end of the string up to the other, it reflects back, and it just keeps reflecting. And there's an interference that happens and things like that to make these specific frequencies. But so anytime there's a disturbance or a vibration in a material, a wave will transfer through it. Sit at a table and put your ear on one side of the table and ask someone in your house just to tap the other side. How do you think that got there? If you feel the vibration or you put your hand on and have someone hit the table, you'll feel the tap that the person did on your hand. Well, how did it get there? Well, it transferred through the wood or through the material to your hand as a wave. It transferred the energy to you. How do you think you hear people in a different room when the door's shut? Well, the waves from your vocal cords vibrate the air. The air moves outward, hits the door, vibrates the door. That vibration goes through the door as a wave, hits the other side, and then the door vibrates and hits the air, and that air transfers the energy as a wave to you, into your ear, which transfers into your eardrum, which taps on a little your eardrum. Basically is like a piece of skin. It's not skin, but and it vibrates and taps on a little hammer and an anvil, and it transfers into electrical energy, and you can hear. Right? It's all about transferring energy through mediums and progressively, and it can travel from one medium to another medium to another medium to another medium to another medium all the time. This is something that always happens. Okay. There are three types of waves. We're only going to focus on the first one and a little bit of the second one, and the other ones are done later. So the very first type that we're going to talk about are mechanical waves. They require a material medium. Okay, so they have to travel through a medium. That means like water waves, sound waves, waves in springs or ropes, and then comma forever. I can just go on about all the different places you can transfer energy through a medium as a wave. Electromagnetic waves. These are weird. It's literally just light, electromagnet. Remember, in our first unit, we talked about electromagnetism, which is that electricity can produce magnetism and magnetism can produce electricity. Michael Faraday came up with this revolutionary idea that electricity and magnetism combined is what light is. He made that hypothesis, and James Clerk Maxwell, on basically, I think Faraday was in his 90s, and James Clerk Maxwell proved through all of his mathematics that light was in fact an electromagnetic wave that traveled at a very specific speed, the speed of light. And that vindicated Faraday for all of the work he'd done and all the hypotheses he had made, that he had said from the beginning that electricity and magnetism was light. These are weird because they don't actually need anything to travel through, right? There's no air in space, yet light can get to us from the sun. How is that possible? Well, because those waves can travel without requiring a material for them to travel through. Now you have to learn about photons and light, and and particle wave particle duality, but that's not until grade 12. So light waves, radio waves, X-rays. I shouldn't even split them up because radio waves and X-rays are light, right? They're just different frequencies of light. Radio waves have big waves, X-rays are small waves. And visible light is just sort of in the middle somewhere. So it's all about the wavelength, and we're going to learn about that later. The last type are matter waves. They're particles of matter that wave when moving. So you need quantum mechanics is needed to describe these waves. Electrons and other particles show wave-like behavior under certain circumstances. In fact, they it's hard to tell an electron is it a particle or is it a wave, and how does it behave? And it often behaves like a wave, which is very strange. And in fact, the quantum realm is just something else, and it really is tied exclusively to waves. And you will learn all about this in university, whether you take chemistry, physics, engineering, or whatever. You have to learn about it because it is so important and fundamental for the way our universe works. So mechanical waves is where we're going to focus on, and mechanical waves and sound. We will leave these trickier types to something to do later. All right. There are two types of mechanical waves. Okay. In fact, there are two main types of mechanical waves, and you can look back to your document and you can start filling some things in here as well. Transverse waves. All right. So transverse waves are waves that travel up and down. Okay. And the particle movement, so in any particular particle movement is up, then down, up, then down. The wave itself propagates in one direction. So the wave energy movement is to one direction. But the particles themselves only go up and down. Imagine that you're in a stadium and the stadium does the wave. You don't, like the wave, you can clearly see the wave going all the way around the stadium constantly. But the particles, the people, stand up, sit down, stand up, sit down, stand up, sit down. They don't move with the wave, right? It's really weird to think about. Like they just go up and down, but the wave moves and the energy moves around the stadium. That's how waves of this type work. A top part of a wave is called a crest or a peak. A bottom part of a wave is called a valley or a trough. And the particle movement is up and down, and the wave energy moves at a very particular speed based on the medium. You might want to even just write that down somewhere, that the speed of the wave is based on the medium exclusively. It's not about how much energy you put into it. It is literally just what type of material that that medium is made out of. Let's take a look at a quick little video of this and see if, okay, there we go. So you can see that the wave, if you follow a piece, see my cursor, it's moving to the right. So I start here, it moves at a very particular speed. We could measure this distance and time how long it takes one of these to go across and figure out the speed of this wave. But if you look at any individual particle, it just goes up and down, 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 up. I'm going to annoy you if I do that. So it just keeps going to the right. Okay, and you can see that the particles individually go up and down. The crest moves as do the troughs. Okay, so that is clearly a transverse wave. Okay. This drawing, there's a box on your sheet. Pause this video and draw this in. Show the particle movement in a different color, label a crest or a peak, the valley or the trough, and write in which direction the wave's moving. You could even put a V for the speed. Okay, so key features, particles move up and down, wave energy propagates, moves forward at a very specific speed, and then on the side of your sheet, right, you need to include this, not this, you need to include this little piece at the bottom. The wave speed, we would do this in class as an experiment, but for right now, I'm just going to explain to you. So the speed of the wave is dependent on the type of material or the medium that the wave is traveling through, not on the amount of energy or the amplitude, or which is the size of the wave. So the amplitude is how big the wave is. A big amplitude is a big wave. Small amplitude, small wave. Turns out it doesn't matter if you have a slinky and you make a huge wave, or if you do a small wave, the wave will travel at the exact same speed through the material, regardless of how much energy you put into it. More energy, more amplitude, less energy, less amplitude, the wave speed stays the same. Maybe flip that sheet over and just write this gigantic on your sheet. That the dependency of the wave speed is only on the amplitude or the energy that you put into it. All right, so we got the transverse moving up and down, wave propagates forward at a very specific speed. Here's some transverse waves. Now, I'm very young in this video, so, oh, come on. I think there's music, but.
Wave is the wrong way.
There is, yeah, you can't hear the video.
Modes of transportation. Yeah.
This is my grade 10 class. My hair was not gray at the point. And now my student teacher, not my student teacher, I had a student helping out in my class from a bigger grade.
Oh yeah. Oh, look at
He had a big amplitude wave, which is pretty cool. And it's too bad you can't hear the slow motion effects in there and the sounds. That was 2006. That's quite some time ago. 14 years. Oh, okay. So anyways, longitudinal waves or longitudinal waves, whichever way you want to look at it. So these particles move, they're compression waves. So you can add that into your little note there. They're compression waves. The wave energy still moves, but these particles just jiggle back and forth, right? There are areas where the particles are compressed together, and there are areas where the waves are rarefacted, or there's lots of space between them. And that area is called rarefaction. You must know the word rarefaction. Rarefied air, like if you go higher up in the atmosphere, the air gets thinner and thinner because gravity's pulling on it less. Most of the air just sits at the bottom, and so it gets rarefied, meaning further apart. Where it's close to the ground, there's compression. So in this type of wave, there's a compression zone and a rarefaction zone, or there's many of them, in fact. But the wave still propagates. These rarefaction zones and these compression zones move. And the particles just jiggle back and forth. They don't actually move with the material. It's a common misunderstanding and misconception. So the wave energy of the movement is to the right. Let's check out a cool video about this. Here we go. So you can see, watch this little particle. This individual particle just jiggles back and forth, back and forth. But look at the wave. There's a compression zone, and the particles stay compressed. And they move at a very specific speed. This is a very slow speed. And then you can see that here's the rarefaction zone where the particles are further apart. And it also moves at the same speed. So this has compression zones and rarefaction zones, and it moves at a very specific speed based on the wave. So there, see, the wave is moving. The particle jiggles back and forth. The compression zones are in the middle of two compression zones is a rarefaction zone. But you can see they move with the wave at the same speed as the wave, because it is the wave. It is the energy that's transmitting. This is what sound does. This is how particles of sound and particles of air move. When you talk, they crunch up in these very specific wavelengths and frequencies, and then they just move through the air by compressing the air in front of it. But the particles of air, like if you talk to someone, the particle of air doesn't run over to the other person and say, "Hey, I'm talking to you," right? The particle just jiggles around in the air, but it's the air near your head that's just absorbing that energy and making the sound appear to get to you. Okay, now here we go. So again, draw this in to your chart, pause it, and do that. Okay, key features. The particles in this move side to side. The wave energy propagates, moves forward at a very specific speed. Again, on the back of your sheet in the biggest pencil crayon color you can do, the wave speed is dependent only on the type of material and not the amount of energy or amplitude of the wave that you put in. So it doesn't matter what you do, it will always move at that speed. If you look at a water wave in water, the speed at which waves move, no matter how much energy they have, is always the same for the particular lake, the temperature, the amount of salt that's in the water, the amount of particulate matter, whatever the case may be. It will always move at that very, very specific speed. It doesn't change no matter what. Now, some things that we are going to talk about. This you'll need to do. There's normally a very long sort of thing about this we're going to do tomorrow or the next day, is talking about the speed of waves. And you can just, on the back of the sheet, write these down for now. And then when we do the next activity, when the next lesson, you can, we'll watch some stuff about this. So basically, actually, I'll stop the video here and I'll leave this for another video where we talk about the speed of waves, about heavy mediums and light mediums, and the transfer of energy through mediums. One thing I wanted to point out before we end this is water waves. Water waves are a combination of longitudinal and transverse. So look, they compress and they rarefact, and they also move up and down. So water waves are wild, and that's why you get sick when you're in the water, because you're going up and down and around, and that's why you get this undulating feeling, because the particles are both doing a transverse and a longitudinal movement. Now, people often mistakenly think that the water that they're getting hit with is water from the ocean. Turns out it's actually just the water that's sitting right in front of you. It's just that it's lifting up and moving down, lifting up and moving down. Because of gravity, things that are on here slide to the front, and you can ride the wave inward because of gravity. So you can slide down the front due to gravity and move with the wave. And that's what happens to particles and objects. And that's why they get pushed onto shore. They get pushed on a shore because of the wave moving up, and then gravity, they slide down. They almost surf the wave into the shore. But it's not the water that's coming to you. It's the same. The water just stays in the ocean. It's the energy of the wave, and the objects that are on it slide down due to gravity towards you. And then you feel sick because it's not just an up and down movement or a side to side. It's an up and forward. And that's why you get that sensation from it. It's pretty wild. That's a good little extension to what we're doing. All right, so that's it. And I'll move on to what happens to waves during when they move from one material to another material in tomorrow's lesson.